this tape, we will look at some basic functions which occur frequently in more advanced math courses. By knowing how to graph a wide variety of functions, we'll be better able to illustrate new mathematical concepts when they occur. Okay, now in earlier videotapes, we learned how to graph parabolas. Basically, we have two main types. We have parabolas of the form y equals kx squared, where k could be positive or negative. These are the parabolas that are symmetric with respect to the y-axis and that have vertex at the origin. When k is positive, the parabola is opening upwards. When k is negative, the parabola is opening downwards. For example, we might have the parabola y equals x squared. Y equals 1x squared. K is 1. It's positive. The parabola is opening up. Okay, it's easy to see, obviously, that y can never be negative, so there is nothing happening here below the x-axis. Y is equal to x squared. It therefore cannot be negative. Everything is happening above the x-axis or at the origin. Now here, if k is negative, we could have, for example, y equals minus x squared. Minus 1 times x squared, k is minus 1. It is negative. The parabola has vertex at the origin and opens downward. Here we notice that y can never be positive. Negative x squared could never be positive, so there is nothing happening above the x-axis. Okay, now we can also have parabolas of the form x equals ky squared, where k is positive or negative. For example, a parabola like x equals y squared would have vertex at the origin and open to the right, like that. We notice, in this case, when k is 1, that x can never be negative, and therefore nothing happens to the left of the y-axis. Similarly, x equals minus y squared, parabola having vertex at the origin and opening to the left. We notice that x could never be positive. Therefore, there is nothing happening to the right of the y-axis. All right, now the first two parabolas that I sketched, okay, these are graphs of functions of x. Okay, we know we have a vertical line test, which tells us that this is a graph of a function if vertical lines drawn at any point in the domain of the function do not cut the graph more than once. Okay, that is, for every x, there should be one and only one y value that is associated with it. When we pick a vertical line, we are really picking an x value. If we're to cut the graph in more than one spot, that would mean for that x value, there is more than one y value associated with it. These are functions of x. These are not functions of x. Okay, later on today, we're going to come and look at these parabolas and see if we could consider, say, just the top half of this parabola or the bottom half, and consider that as a function of x. But as it stands now, these graphs fail the vertical line test. Here we have a vertical line which cuts the curve in more than one spot. So these are not functions of x, but it's still useful for our work to understand them as parabolas. Now, after determining the basic type, a few points can be plotted to determine how wide or narrow the parabola is. For example, let's say we have y equals 4x squared. We're interested in comparing that with y equals x squared. We can make a little table of values, both cases. These are both parabolas of the form y equals kx squared, where k is positive. All right? Here, for example, if x is 0, y is 0. If x is plus or minus 1, y is 1. If x is plus or minus 2, y is equal to x squared, y is equal to 4. Over here, if x is 0, y is 0. It goes through the origin as well. However, if x is plus or minus 1, y is equal to 4. If x is plus or minus 2, y would be 4 times 2 squared, 4 times 4, or 16. All right. Now y equals x squared. Let's start by sketching that. Goes through 0, 0, 1, 1, minus 1, 1, 2, 4, and minus 2, 4. Okay, looks something like that. We could plot a few more points. That's the basic idea. Now let's sketch y equals 4x squared on the same set of axes. Goes through the origin. Now it goes through the point 1, 4, and minus 1, 4, 2, 16, and minus 2, 16. Let's sketch it in by a dotted line. Okay, so we have y equals 4x squared by the dotted line, y equals x squared indicated by the heavy line. Okay, so basically, they are both parabolas, vertex at the origin, opening upwards. And by plotting a few points, you could determine which one is wider, which one is narrower. Okay, they're in the form y equals kx squared. And we see that the y equals 4x squared is a narrower parabola here. Okay, let's try another one. Y equals 2x squared minus 8. Okay, this is also in the form y equals kx squared. And if we were to get the intercepts of this parabola, it would help us to locate it a little better. All right, we can make a table of values. If x is 0, y is minus 8. If y is 0, we'd have 2x squared minus 8 equals 0. 2x squared is 8. X squared is 4. X is plus or minus 2. So the x-intercepts are plus and minus 2, and the y-intercept is minus 8. Goes through 0, minus 8, 2, 0, and minus 2, 0. Okay, this coupled with the fact that we know it's a parabola of the y equals kx squared variety. Smooth it out a little. Looks something like that. Goes through 2, 0, minus 2, 0, 0, minus 8. We know it's of the y equals kx squared variety where k is positive. So it is opening upwards. The points, here we just plotted, in this example here, we knew that the only intercept was the origin. If x was 0, y was 0. If y was 0, x was 0. And a few points to determine how wide or narrow it was. Here, we were able to get all the intercepts. We were able to get intercepts at 0, minus 8, 2, 0, and minus 2, 0 to help us locate the parabola. And we could also figure out how wide it was. But if you know the basic types, okay, the rest is just to help you locate it on the coordinate axes. X equals 4 minus y squared. Now this is of the form x equals ky squared, which means it's a parabola opening right or left. However, k is minus 1 in this case. It's of the form basically x equals minus y squared. So it will be opening to the left. Let us get some intercepts for this. If x is 0, 4 minus y squared is 0. Y squared equals 4. Y is plus or minus 2. If y is 0, x is 4. And we have 1, 2, 3, 4, 0 is a point on the curve, 0, 2, and 0, minus 2. And as I said earlier, the parabola is opening to the left. Okay, now, this is not, as I mentioned earlier, this is not a function of x because it fails the vertical line test. Okay, if we draw a vertical line and it cuts the graph in more than one spot, then this could not be the graph of a function. Okay, if we try to solve this equation, x equals 4 minus y squared, if we try to solve it for y, let's see what we get. We get y squared plus x equals 4. Y squared is 4 minus x. And from this we get that y is plus or minus the square root of 4 minus x. And when we write the equation in this form, the multivalued nature of y becomes obvious. If, for example, x would be equal to 1, y would be plus or minus the square root of 3. In other words, it would be when x equals 1, there are 2 y values associated with it. Okay, so it becomes very clear that it's not a function of x when we look at it in this form. Okay, now we still have, sometimes we would still like to deal with a curve like this. So what we do is we isolate the top half, we separate the top half and the bottom half. We talk about the graph of y equals the positive square root of 4 minus x and the graph of y equals the negative square root of 4 minus x. If you don't see any sign in front, it means the positive square root. And the way we handle this is the following. The best thing to do would be to square both sides and to recognize that if you squared both sides of this equation, you would get y squared equals 4 minus x. Sketch that. Get the entire parabola. As I said, this is a parabola with vertex at 4, 0, opening to the left. Now, if it's y equals the positive square root, that means the top half only of the parabola. This would be the graph of y equals the positive square root of 4 minus x, and the graph of y equals the negative square root of 4 minus x would be the bottom half only of the same parabola. Okay, so anytime you have to sketch the graph of a function involving a radical, say a square root like this, square root sign, the best thing to do would be to square both sides. Okay, if you can graph the function in the squared form, and very often it's easier to recognize in that form, then simply say, well, if y is the positive square root, I will take the top half only. If y is the negative square root, I will take the bottom half only. If you ever have a situation where x is the positive square root, you might take the right half. X is the negative square root, you might take the left half. By the way, on these functions, now these are functions of x. We could find the domain. We know we have, so we know right away the domain is restricted. 4 minus x has to be greater than or equal to 0 in either of these cases. You cannot take the square root of a negative number. So 4 minus x has to be greater than or equal to 0, or 4 is greater than or equal to x, or x has to be less than or equal to 4. Now we do notice the domain here. Which x values can be substituted into the function? All those that are less than or equal to 4, and the graph starts here at 4. For x equals 4, and there are values here, but there is no picture when x is greater than 4. If you were to substitute a value of x greater than 4, you would get the square root of a negative number for y, and you could not plot that. So the picture starts here at 4 and goes to the left, but there is nothing when x is greater than 4. Okay, let's try some more examples. Y equals the square root of x minus 4. Okay, once again, when I see a square root function like this, the best thing to do would be to square both sides. And if you can graph this one, then you know if y is a positive square root, we'll take the top half only. Okay, when I square both sides, I recognize this to be a parabola. This is because x is not squared, y is squared. Right? If neither one had been squared, it would have been a straight line. They're both squared. It could be a circle, ellipse, or hyperbola. Okay, but when one is squared and the other one isn't, then we know we have a parabola. It's of basically the x equals y squared variety, which was one of the types that we considered. And it will be a parabola that is opening to the right. Let us try to find a few points on the curve. If we let y be 0, we get x equals 4. If we try to let x be 0, we get y squared is minus 4. We cannot solve for y. There are no y-intercepts. Okay, to get some more points on this, we might try x equals 5. If x equals 5, y squared would be equal to 1. Y would be plus or minus 1. We notice that the domain of this function is restricted. X minus 4 has to be greater than or equal to 0, or you can't substitute the x value in. That is, x has to be greater than or equal to 4. That would have told us that we could not let x be 0. Now we try to sketch the entire parabola. It goes through, as I said, 4, 0. There are no y-intercepts, but that goes along with the reasoning that we had before, that it is opening to the right. We do have another point to help us to get the dimensions here. 5, 1, 5, minus 1. Okay, now that is the graph of the entire parabola, which of course is not a function of x. However, we were asked to graph y equals the positive square root. So after you finish this, you then say if y is the positive square root, it is the top half only. This is the graph of y equals the positive square root of x minus 4. Okay, but square it and use plot points on the squared curve to get the whole parabola, and then if it's a positive square root, you'll take the top half, the negative square root, you'll take the bottom half. For our next example, let's try y equals the negative square root of 4 minus x squared. Once again, I see a square root involved in the function, so I'm going to square both sides. When I do that, I get y squared equals 4 minus x squared. Okay, now some people may be upset what happened to the minus sign. Let me just remind you, if it had been y equals, say, the negative square root of 7, and I asked you to find y squared, that would be, y squared would be the negative square root of 7 squared, or the negative square root of 7 times the negative square root of 7. Now what happens? The negative times the negative becomes a positive. The square root of 7 times the square root of 7 just gives you 7. In other words, a negative number squared becomes positive, and what you get is just what's under the radical. And that's precisely what I did over here. Just think of this as negative the square root of something. But a negative times a negative will be positive. And what you'll get when you square this is that it'll square out, you'll just get what's under the radical. Okay, so the answer is not minus 4 minus x squared or any version of that, variation on that. The minus times the minus becomes a plus, and all you get is what's under the radical. The minus is there just to tell us that at the end, it'll be the bottom half of whatever curve we get. Okay, now what kind of a curve is it? We can bring x squared over to the other side, and we recognize, well, x and y are both squared, and furthermore, they have the exact same coefficients, and what we have here is a circle. The center at the origin, and radius 2. You can plot some points, but this, I think, is pretty well known to most of you. In other words, if y is 0, x squared is 4, x is 2, and minus 2. If x is 0, y squared is 4, y is 2, and minus 2. This is a circle centered at the origin, radius 2. Okay, now that's what this is. Now what about what we started with? Y is the negative square root. That means the bottom half of that circle only. So after we've gotten the picture, we have the picture here, we then say, but it was, y was the negative square root of 4 minus x squared, so it is the bottom half of this circle only. The domain is between minus 2 and 2, the range between minus 2 and 0. For our next example, we have y equals the negative square root of 36 minus 9x squared. Once again, we square both sides to get a feeling for what kind of a function this is and what kind of a curve this is. The minus times the minus will be a plus. Square root squared will give you just what's under the radical. Adding 9x squared to both sides, we get 9x squared plus y squared equals 36. X and y are both squared, and therefore it's either a circle, ellipse, or hyperbola, since the coefficients of x squared and y squared have the same sign, but they have the same sign. Okay, but they have different values. We have an ellipse here. And we can make a little table of values. If it would be 9x squared plus 9y squared equals 36, that would have been a circle. Okay, when they have just the same sign, okay, but the coefficients are not equal, then we have an ellipse. If x is 0, y squared is 36, y is plus or minus 6. If y is 0, 9x squared is 36, x squared is 4, x is plus or minus 2. We have an ellipse going through the points 0 minus 6, 0 plus 6, 2, 0, and minus 2, 0, going through these 4 points. These are the intercepts. Okay, that is the graph of 9x squared plus y squared equals 36. However, we say, what did we start with? We started with y equals the negative square root of that. Therefore, y can't be positive. There can be no curve above the x-axis. And we erase this portion in here. So it's the bottom half of this ellipse only. Here is y equals the negative square root of 36 minus 9x squared. The domain from minus 2 to 2, the range, the y values that come in when you plug in those x values between minus 6 and 0. Okay, for our next example, y equals the positive square root of 9x squared minus 36. Once again, we will square both sides to see what we get. We can subtract y squared from both sides of the equation and add 36 to both sides, giving us 9x squared minus y squared equals 36. I've added 36 to both sides of the equation. Okay, we see that we have an x squared and a y squared, and the coefficients have opposite signs. Okay, this points us out as a hyperbola. Now we can get the intercepts in this case. If y is 0, 9x squared is 36, x squared is 4, x is plus or minus 2. If x is 0, we get that minus y squared is 36, y squared is minus 36. There are no y-intercepts. Okay, well, this is a hyperbola opening to the left and right. That explains why there are x-intercepts but no y-intercepts. Let's try to sketch the graph. Now, when we're sketching the graph of a hyperbola, we have a nice way of doing it. We put down the x-intercepts, which are 2 and minus 2. By the way, this is just a review tape on this. Okay, we're not concentrating on the hyperbola. If you don't know how to sketch a hyperbola, there is a review tape there is a tape just on the hyperbola. All right, the x-intercepts are 2, 0, and minus 2, 0. Now, there are no y-intercepts. For the moment, let's pretend this had been a plus sign. If this had been a plus sign, the y-intercepts would have been plus 6 and minus 6. Even though those are not intercepts, I'd like you to put those points down. Okay, now I'd like you to draw a rectangle going through the 4 points that you see on the blackboard. It would look something like this. The diagonals of this rectangle should now be sketched in. These are useful guidelines for sketching the hyperbola. Once again, I put down the x-intercepts. There are no y-intercepts on the hyperbola, but I pretended for a moment that this was really a plus sign, and there were y-intercepts of 6 and minus 6. Okay, I drew a rectangle through those 4 points. By the way, those 4 points were the same 4 points that we used. Those were the intercepts that we did have for the ellipse over here. If you remember the ellipse, it went through 2, 0, minus 2, 0, 0, 6, and 0, minus 6. In other words, that ellipse would fit right in here, in that rectangle. Okay, but now we're talking about a hyperbola. Once we have drawn this rectangle and the diagonals, we now remember that they did have x-intercepts but no y-intercepts. The hyperbola is now drawn through the x-intercepts, asymptotic to the diagonals of the rectangle. These are guidelines telling us sort of how wide or narrow to make the hyperbola. Now that is, okay, there are a lot of lines here, but here we have the graph of the hyperbola. Now, what do we want? We want y as the positive square root, that is the top half only. So I'm going to erase the bottom half of the hyperbola. Furthermore, I'm also going to erase the guidelines just so that you can see what we get as a final answer. So what we get is just the top half of this hyperbola with intercepts of 2 and minus 2 on the x-axis, no y-intercepts, the top half only. Y can never be negative since we have the positive square root. Y can be 0. For example, if x is 2, y is 0, but it can never be negative. All right. Now, this is an example of a hyperbola, or actually the top half of a hyperbola. There are also other ways that we might see a hyperbola drawn. Y equals k over x is the equation of a hyperbola as well. If k is positive, we get a hyperbola in the first and third quadrants. If k is negative, we get a hyperbola in the second and fourth quadrants. Now you might think that this looks nothing like the example that we just had. And why am I calling it a hyperbola? The problem is that the one that we just sketched looks something like so. It was symmetric with respect to the x-axis and the y-axis. What we have here is the hyperbola tilted or rotated so that now it's symmetric with respect to the 45-degree line and the 135-degree line. Whereas if you were to turn your head this way, okay, if you would pretend that these were the coordinate axes, you see, yes, you do have the hyperbola that we had over there. Okay, so this is the graph, this is an equation of a hyperbola, although it's not symmetric with respect to the coordinate axes anymore. Okay, now how did I come up with a picture like this? Let's look at an example. For example, k is 1. Y equals 1 over x. Well, the first thing we notice is that if x is positive, y must be positive. Therefore, there can't be anything down here in the fourth quadrant, because these would be points that had x positive and y negative. Furthermore, if x is negative, y would be negative. So there can't be anything happening up here in the second quadrant, because these points would have x negative and y positive. So all the action is happening in the first and the third quadrant. We notice that there is trouble at 0. You cannot substitute 0 into this function. 0 is not in the domain of the function. As x gets close to 0, through numbers that are bigger than 0, you can substitute and you can make a table of values. For example, if x is 1/10, y is 10. If x is 1/100th, y would be 1 over 100, y would be 100. The y values are getting larger. Similarly, as x gets close to 0, through the negative values, for example, minus 1/10, y would be minus 10. Minus 1/100th, y would be minus 100, and so on. Also, when x gets very big, y gets close to 0. If x is 100, y is only 0.01. If x would be 1,000, y would be 0.001, and so on, getting very close to 0. And the same thing here. As x gets very negative, y is getting close to 0. Okay, and we get a picture like that. When y equals, for example, say minus 2 over x, the action switches from the first and third quadrants to the second and fourth quadrants. Here we notice when x is positive, y must be negative. Negative over a positive is negative. So there is nothing happening in the first quadrant. Also, when x is negative, y is a negative over a negative, y must be positive, so there is nothing happening in the third quadrant. Okay, now I'd like to consider slight variations on these rational functions. For example, y equals 1 over x minus 2, and also y equals 1 over x plus 3. Okay, now these are similar to y equals k over x, which we know, if k is positive, is a hyperbola of this basic configuration. The difference between these hyperbolas and the one that we sketched originally, say y equals 1 over x, is that here the trouble occurs at x equals 0. In other words, we would have division by 0 if x were allowed to be 0, and therefore there can be no y value when x equals 0, and x equals 0, or the y-axis, was an asymptote for this hyperbola. In the one I've drawn over here, in the equation I've written down over here, the trouble is not happening at 0. For example, if x is 0, y is minus 1/2. That's just perfectly fine. The trouble is at x equals 2. If x is equal to 2, then you cannot find a y value. That is, 2 is not in the domain of the function. So if we were to go over to x equals 2 and sketch it in, this would be an asymptote for this hyperbola. The other asymptote would be the x-axis. It would basically be of the form y equals k over x, where k is positive. So the action would be happening in the upper right-hand corner and in the lower left here of this new coordinate system, which I've sketched in. That is using the dotted line and the x-axis. What this has done, in effect, is to take the action and move it 2 units to the right. Take what's happening in this hyperbola here and shift the whole thing 2 units to the right. So instead of having trouble at x equals 0, as we had over here, we pick the whole thing up, we move it over to 2. so that the trouble spot is now x equals 2. Similarly, we can work it out over here. Here, the trouble is now occurring when x equals minus 3. That's when we cannot substitute in. For x equals minus 3, we cannot substitute in that x value. There is no y value. The asymptote has switched over there. It is still a hyperbola, basically, of the same configuration. It's going to look something like so. In other words, in the upper right and in the lower left sections. By the way, you can check this out a little by looking at the y-intercept. Here, if x is 0, y is minus a half, which makes sense. Here, if x is 0, y is a third, okay, which also makes sense. It is cutting it, at least the y-axis, in the right spot. Of course, you can make a table of values, including some more points, to get a better idea of how wide or narrow it might be. But this gives you the essence of the curve. Of course, if this had been a minus 1 over x minus 2, I would have drawn it in the upper left and in the lower right portions of this new coordinate system. The minus 1 would have put the emphasis on the second and the fourth quadrants, that is, of the new coordinate system here. Okay, let me show you for my last example, let me show you another basic curve that you may run across in more advanced math courses. Y equals k over x squared. Okay, we've seen y equals k over x. Those were hyperbolas. Y equals kx squared. Let's consider if k is positive or if k is negative. For example, we could have y equals 2 over x squared, or y equals minus 1 over x squared. Okay, y equals 2 over x squared. First thing we notice is that y can never be negative. 2 over x squared can't be negative, so there is nothing happening down here. And by making a table of values and plotting points and investigating what happens, we can see that, first of all, 0 is not in the domain of the function. And what we get is something like this. Should be a little more symmetric. Of course, to figure out how close you are to these axes, you really should plot some more points. But it's basically in this form. Remember what y equals k over x looked like? It was in the first and the third. Well, the k over x squared, and it doesn't allow for negative y values. In this portion, it sort of has been flipped over. And y equals, say, minus 1 over x squared would be similar to this, except here, y could never be positive. Also, once again, 0 is trouble here. 0 is not in the domain of the function. X equals 0, or the y-axis is an asymptote of the curve. And that brings us to the end of this tape.